Okay, so last day today, guys, of the physics units. Okay, I'm actually going over probably one of the easier things in the unit today, and that is efficiency. And that was part of what we were doing with the lab we did last week. Okay, with the cart there, and trying to see just how much of the mechanical energy in the form of potential energy that we put into the system was actually going to be converted into kinetic energy, okay, which is the movement of the cart. Okay, and I think if you've done any of those calculations, you're probably finding that's a pretty small percentage, right? If you haven't started doing that, you will. Um, the reality of it is that in the real world, yes, energy is conserved, but that doesn't mean that it does what you want it to do. Okay, it's accounted for, it's still in the system or the surroundings, but it probably didn't do the useful work that you had planned for it. Right? So case in point could be if you are, let's say, trying to push a really heavy, let's say, wheelbarrow full of stuff, okay, from one place to another. All right, you do a lot of work in pushing a heavy wheelbarrow, especially if you're pushing it uphill. Okay, so you're changing its kinetic energy, you're changing its potential energy, but is all of your work going into moving the wheelbarrow? Where is some of it going? Some of it could be sound. If the wheel on the wheelbarrow has got points of contact, it's going to squeak. Okay, so there could be some sound there. All right, where else could it go? Friction. Yeah, there's tons of friction. Okay, and so you're going to lose some energy there. Sound is usually produced by friction. Heat's usually produced by friction. If it's really bad, you can get sparks and then get light. Okay, as a source of energy lost to friction as well. Okay, the other part of it though is just even within your own body, you're not getting all the energy that you're using actually even to the wheelbarrow. Okay, never mind the wheelbarrow wasting some of it. A lot of it is wasted within your own body, in your own joints, okay, within your own muscles and things like that. I mean, pushing a wheelbarrow, if you have to push it very far, you probably start breathing heavily, okay, you probably start sweating, right? All of those are signs that not all of the work you're doing is going to the wheelbarrow. A lot of it's turning into what? If you get hot, it's because of heat, yeah, thermal energy, right? A lot of the inefficiencies in systems has to do with the production of thermal energy, okay? The loss of energy as heat. Right? That's where the bulk of it goes. Okay, so the purpose of any machine obviously is to convert the initial energy, whatever it was, and for us in our society most of the time that's chemical energy of some kind, okay, into the type of energy needed to do the work that you want to have done. All the other kinds are considered wasted. Okay, they're not destroyed. The energy is not destroyed because we know we can't do that. It's just not doing what you want. Okay, so the initial energy source we call EI. Okay, and that's called the energy input. Okay, so that is the bigger of the two numbers. Okay, the input energy is always going to be the bigger of the two numbers. The other number, okay, that we have in there, okay, is our useful work output, okay, and that is essentially how much actually gets done, okay, and then there's also useful energy output, which we'll talk about here in a minute, okay. So what we want to look at is a typical example of something we use every day. Now, let me put it this way. If you went to a doctor to find out, let's say you had something wrong with you and wanted to figure out what it was, would you go to a doctor who was only right 12% of the time? Would you go to anyone who was only right 12% of the time for anything? No. Okay. Would you invest money in something that lost 78% of your money? You do it every day. In fact, you invest your money in something that loses 88% of your money. Because you get in your car and you drive to school, you drive to work, you drive around. Okay, guys, the typical, let's say, full-size passenger car runs around 14 or 15% efficiency. Right? So if you put $100 worth of gas in that car, only $15 of it actually results in the car moving forwards. The rest of it is lost to the surroundings in some other form, usually heat. All right? How many people have some working knowledge of how their car works? Okay. I'll give you a kind of a quick explanation here. Your car has pistons in it that move up and down. Okay? When the gas gets gas and fuel, there's a mixture of it, which your car kind of mixes, the computer mixes it for you. Okay? It gets into the cylinder, then there's a little spark plug on the top of the cylinder. Okay? And it just makes a little electrical arc that ignites the fuel. All right? And when that fuel ignites, the expanding gases push the piston down, and that's what drives your cars. These expanding gases pushing the piston. The pistons are connected to the drivetrain that turns your wheels. All right? Expanding gases, when you blow them up, which is essentially what you're doing with gasoline, you're causing explosions to happen all the time inside your motor. Okay? Do they generate a lot of heat? Is the heat used by your car? Nope. Only the expansion of the gases is used to move your car. The heat, the bulk of it, has to be essentially gotten rid of so that your car doesn't melt down. So your car has a cooling system on it. Okay? You can hear this sometimes. You stand next to a car that's just kind of idling. You can hear the fan turn on sometimes. All right? And there's a big thing at the front of your motor called a radiator. Okay? In there is coolant. Okay? It's full of this green kind of looking stuff, okay, called antifreeze, right? And it's in there, and it circulates throughout your car. There's a water pump, okay, that pumps this coolant through the engine block of your car in order to absorb the heat that's produced by the explosion of gasoline. If it was not for that system, your car would overheat. Okay? And if it overheats, the metal it's made out of expands to the point where the pistons can't move up and down anymore, and it'll seize, and then stuff breaks, and then you're in really big trouble. All right? So you have to be very careful, okay, with the temperature of your car. Well, that system alone takes 1/3 of the energy in your fuel. To run the system that keeps your car from destroying itself takes 1/3 of the energy you put into it. So 33 of that $100 is used just to drive the cooling system of your car. Okay? Another 33% of it is lost by your exhaust system, because the gases that come out of your car are hot. Okay? And that energy isn't used to do anything. So we've used two systems, neither of which drives your car forward, and we've already used up 2/3 of the energy in your fuel. Haven't moved yet. Okay? Those two systems right there are the two biggest consumers of energy within your car. It's sad, really, when you think about it. Okay? The drivetrain. Okay? So the drivetrain would include things like transmission, all-wheel drive systems, limited slip differentials, things like that. Anything that results in the essentially transfer of mechanical energy from the motor to the wheels. All right? So that's 10%. Okay? And there's a lot of friction in there. Okay? It's a lot of moving parts, so that's why it's 10%. Your accessories. 4%. Your accessories are things like your rear window defogger, air conditioning, power windows, door locks, heated seats, whatever. Those are your kind of accessories, okay? Your stereo. All right. Now, if you have one of those stereos where people like a half a mile away know you're coming, okay, you probably have a second alternator on your car to power it. Okay, at least I knew a guy who did. Okay, he had his stereo was so big that the alternator on the car, and that's the part that generates electricity. It's a little generator that's just attached by a belt. Okay, he had to put a second one on to run enough power for his stereo. Okay, so he probably was using more like 8% to power his accessories. If he turned on the stereo, the engine labored. Okay, because it would needed so much power to run the stereo. It was also pretty cool. He would do this thing called the loonie dance. He would toss a loonie on top of his car. He was an old beater, so it didn't matter that it scratched the paint. Then he would crank the stereo, and the loonie would bounce all over the top of the car, which was really cool. And then he turned it up just a little bit louder, and then the back window shattered. Yeah. And he's like, oh, cool. I'm like, you don't have any idea how much a back window with a rear window defogger and it costs to replace, do you? Yeah. Anyway, so those take up another 4%. And then various miscellaneous internal friction is another 6%. That leaves us with 14% of the energy in your gasoline actually doing the job you intended it to do. All right. Now, that's for, kind of let's say a little bit older vehicle. Vehicles are a little more efficient now. They probably run a little closer to 20%. If you have a hybrid vehicle and you're using it in the right way, it probably runs a little closer to 25%. Okay, maybe even upwards of 30. Okay, but most cars that are just strictly internal combustion, and the bigger they are, the less efficient they're going to be. Okay, run around 15 to 20%. Okay, now, does anyone have a hybrid car? Parents have a hybrid car? Anyone running like a full electric? I know there's one Chevy Volt running around town I've seen. That's the full electric car. Okay, a hybrid car has both a internal combustion engine, so a gas engine, and it has electrical motor or motors. Okay, and people get the idea that this is going to be really efficient, and it can be as long as you use it in the proper way. A hybrid vehicle on the highway gives you absolutely no benefit. Okay, a hybrid vehicle on the highway gets about the same gas mileage as a regular internal combustion vehicle does. The benefit of a hybrid car is stop and go traffic. Okay, where you consume the most fuel is when you're accelerating. Okay, so when you've stopped and then you have to accelerate again, that's what takes the most fuel. So what a hybrid car does is when you push down the pedal to accelerate, the electric motors assist the gas motor. Okay, so the gas motor doesn't have to work as hard and you don't burn as much fuel. Where do the electric motors get their energy from? Batteries. How do we charge the batteries? Well, if you have a plug-in hybrid, you can plug it in and they'll be ready for you in the morning. But most hybrid vehicles, the gasoline engine is what charges the battery. Okay, so as you drive, you charge the batteries. And then when you need the electric motors, they kick in and draw from the batteries, and then they shut off when you don't need them anymore, and the gasoline engine will recharge the batteries. Okay, so it's reasonably efficient, provided you're using it in stop-and-go traffic. Okay, then it works. The disadvantage, obviously, okay, is that batteries have lots of chemicals in them. Okay, and there has been a bit of an issue with what do we do with these batteries once they stop working and have to replace them. Okay, so they can work. Okay, they can be very efficient if you do use them in the right way. A few automakers have even tried to harness some of the heat that the car produces to help to charge the batteries. We talked about this. We talked about the thermocouple. Okay, the very first day of the unit, and that converts heat directly into electricity. Honda was the first manufacturer to do this. They put thermocouples in the brakes of the cars. Okay, so they essentially made the rotor, which is the silver part you can see if you look through the wheel. Okay, they put thermocouples in the rotor, and then when people would apply the brakes and the rotor got hot, it would generate electric current that would go back and charge the batteries. Now, that's thinking, because where was that energy going to go otherwise? Just to the surroundings, right? It would have been completely wasted, right? So they're harnessing some of it, a small amount, to help charge the batteries. And again, that helps to increase the efficiency of the car because that energy would have otherwise been wasted. Okay, so what we're trying to do with the development of technology is make things more efficient. Okay, light bulbs are another example of things that we have made more efficient, okay, over like the last 10 or 15 years. Okay, when I was growing up, there was one kind of light bulb. Right? And that's the old-fashioned kind with the filament inside. Okay, how many people still have those in their house? Probably a lot of you don't know, but okay, they're not all that common anymore. People want the ones that are more efficient. So people got those compact fluorescent ones that look like a coil. Right? They look like a fluorescent bulb, except they're coiled and small, and they're the same size as a regular light bulb. Okay, they're more efficient. They generate less heat. The problem with incandescent, that's the old-fashioned kind of light bulbs, is they make light by making the filament get super, super hot. Okay, and so once you turned them on, like after about 10 seconds, you couldn't grab them with your bare hand. They were that hot. All right, and in a fluorescent bulb, if it's been on for a while, you can still grab it. It's not very hot. An LED bulb, which is the newest variety, okay, they're even more efficient, and you can have them on for hours and hours. Reach up and grab them, and they're still cool to the touch. Okay, so they're using a lot less energy to do the same job. Okay, so a 60-watt light bulb, the incandescent kind, is what you used to use for most applications. You could replace that and get the same amount of light out of a 13-watt compact fluorescent bulb. Okay? Is that a fairly big savings? Okay? A watt, by the way, is a joule per second. Okay? So an incandescent light bulb that's 60 watts is using 60 joules of energy per second. Okay? A fluorescent bulb doing the same job is using 13 joules per second. So it's a pretty big savings. Okay? What's the problem with the fluorescent bulbs? Anyone know what's in them? Mercury. Yeah, there's mercury in them, and people were throwing them away like they were regular incandescent light bulbs, and a lot of mercury as a result ended up in the landfills. Okay, and that stuff doesn't degrade very quickly, so there's a drawback to those. Okay, LEDs are the newest one. You can replace a 60-watt incandescent light bulb with a 4-watt LED. Okay. Now, is it straight across? No. An incandescent light bulb costs you about 35 cents. An LED bulb costs you about $16. Okay, now, it saves you way more than that over its lifetime, but okay, it's a little more to shell out at the beginning. But again, they're more efficient because they don't produce as much heat. Okay, making sense? All right. Okay, so systems with moving parts are always going to lose energy as heat. Okay, which is consistent with the first and second laws of thermodynamics. Remember, the first law of thermodynamics is essentially the law of conservation of energy. Okay, the second law of thermodynamics is that energy always flows from hot to cold. Okay. Okay, so for example, the energy supplied to your body by food energy has to equal all of the useful work done plus all of the wasted energy, which includes heat and the mechanical energy of the parts of your body. So according to the second law, heat flows from hot to cold, and in the process, it can be made to do work. Okay, and that was the idea behind that heat engine that we talked about. Okay, during the thermal energy transfer, most energy is lost to the surroundings. Okay, so the efficiency of a system can never be 100%. Okay, that means you can never come close to getting the energy out of a system that you put into it. Okay. An electric motor runs at about 95% efficiency. Okay, 95%, but they'll still generate some heat. Right? Why is an electric motor so much more efficient than a gasoline motor? Okay, well, I mean, it produces a little bit of heat, but it doesn't, yeah, it doesn't, yeah, you're thinking it doesn't rely on explosions, right? Yeah, there's no internal explosions that make heat in an electric motor. The other thing is that an electric motor, by its nature, has a lot less friction. Okay, how many people have ever seen what an electric motor looks like? Okay, it's lots of magnets. Okay, and they repel each other, so they keep the moving parts away. I mean, there's still some points where there's contact and pivoting and stuff. Okay, but for the most part, the magnets, and that's what makes the electric motor spin, hold the parts of the electric motor apart. Okay, so as a result, it's more efficient. It's the same idea if you've heard of like a maglev train, a magnetic levitation type of train, or like a monorail kind of an idea. Okay, the idea there is that magnets with different polarities, with the same polarity, will be on the inside of the track. So it would be a maglev kind of a train. So you'd have that shape. You'd have a track that looks kind of like this, okay, and then the train would sit over top of it, okay, kind of like this, okay, and this would be the upper part of the train. Man, I can't draw. Okay, so you'd have magnets here and here, and you'd also have magnets here, and they would produce a repulsion, so the train would just float over top of the rail. Okay, now, does that reduce friction? Yeah, because our trains, do they have a lot of friction? Yeah, that's why they're so loud, right? And it's not just clickety-clack, it's like screeching and all that kind of stuff when they go by on the train track, okay? Because that's metal on metal. Okay, there's a lot of friction in there. A train like this would be much more efficient. Okay, they're also much more aerodynamic. If you've ever seen like what monorails in like Japan and stuff, the high-speed bullet trains look like, okay, they're like super aerodynamic and cone-shaped and all of that. Right? So they're using a lot less energy to do the same job just because they're designed to reduce the places where energy is usually lost. All right, so using the formula here for efficiency. So to calculate percent efficiency, you're going to divide the amount of useful work that was done by the amount of energy that you put in to do it. Okay, very simply. You can multiply by 100 after that, but I usually take this multiply by 100 part out just because it's confusing. Okay, when you guys calculate your percent on a test, you just go what I got divided by what I could got, and it gives you a decimal, and you just know that 0.85 means you got 85%, right? Okay, so that's what we're going to do. We're going to just remember that, okay, and forget about this multiply by 100 part. So our formula is going to be, okay, useful work, EM, divided by total work input, okay, or the energy that we had to put in. Which number is always going to be bigger? The last one, right, the one on the bottom is always going to be the bigger number. If you get a number greater than 1 when you do this calculation, you switch the numbers around. Okay? If you get a number greater than 1, you are operating at more than 100% efficiency, which means your machine was making energy as it ran, and that's against the first law of thermodynamics. All right? Okay. Now, some machines, okay, that we use every day involve the conversion of mechanical energy to another form of mechanical energy, and anytime that happens, energy is lost along the way. Okay, so like we said here already, an automobile internal combustion engine, 12 to 15%, an electric engine, 95% or up to 95%, steam reciprocal engines, okay, 50 to 75, steam turbines, around 40%. Okay, and the reason steam turbines have a lower efficiency is the turbine itself can spin easily, but as soon as you put on whatever it's supposed to drive, that's where it loses the energy. So the turbine then is under load and loses efficiency because it's turning something else. Right? So in an electric power plant, when you got the steam going through the turbine itself would be efficient if it wasn't attached to the big generator on the other side. Okay, and then that's going to slow it down. All right, so let's try this example right here. I've got a crane that lifts a load of construction materials from the ground to the second floor of a building. In the process, the crane does 2.3 times 10 to the 4 joules of work. Okay? However, in the process of doing that much work, only 8.0 times 10 to the 3 joules of useful work is actually accomplished. All right? So we've got this number, which incidentally is 23,000. Joules. That's how much work had to be done, okay, in order to get this job done. And the job really should have only required 8,000 joules of energy to do. Okay, everybody with me there? So when I want to calculate the efficiency here, okay, this is going to be my input energy, and this is going to be my useful work, EM. So when I want to calculate the efficiency, it's going to be 8,000, okay, divided by 23,000. All right, so that thing's running at roughly 35% efficiency. Yeah, the crane running at about 35% efficiency. Okay, does that sort of make sense? Now, if I needed to manipulate this equation, so I have percent and then I have EM over EI. What if the question says a motor operating at 15% efficiency does 100,000 joules of work? How much useful work was done? Okay, they would have given me this, the 15%. They would have given me this, okay, the amount of work that was actually done, okay, and they'd want me to look at this, okay, which would be, or find this one, which is the amount of work that would actually get accomplished. Right? So how would I get this by itself? Right, multiply it over to this side, okay, and then do what with the percent? Divide it, right? Okay, and so then we would go from there. All right, everybody with me on that? Okay. All right, so I've got a few here that I want you to do, okay, just to practice that, because I often put 1 or 2 in as a multiple choice question on the test. Okay. Okay, so let's have a look at number 1 here. So I got an internal combustion engine that's operating with an efficiency of 15%. Okay, so I know the percentage is 15, and it's used to do 3.2 times 10 to the 4 joules of useful work. All right, so that is, okay, our bottom number, or sorry, our top number, okay, the useful work, so that's, okay, EM, right, and that is going to be the 3.2, okay, times 10 to the 4 joules. We're looking for the energy input, okay, how much work did I have to put into that? right, in order to make this work. All right, so I know that percentage, okay, equals EM over EI, and I'm trying to find EI here, right? So I'm going to bring EI over to this side by multiplying. Then I'm going to divide by the percentage, okay, which makes sense. If I divide a small number by a decimal, 0.15, do I make it bigger? Yeah, anytime you divide by a decimal, you make the number bigger, and this number should be bigger, okay? Because it's how much work we actually had to do in order to do the useful work we wanted. All right, so when I plug that in then, I'm going to have 32,000, that's 3.2 times 10 to the 4, okay, divided by 0.15, okay? And when I do that, okay, I get 213,333 joules. Okay, is that making sense to everybody? The biggest problem with these is being able to sort out which thing is which, because unfortunately, this is kind of like in chemistry in the mole equation where they had a 3-variable formula and used the same letter twice. Okay, in this formula, they're using mechanical energy twice. Okay, it's just different types of mechanical energy. Okay, for number 2, we'll look at that one as well. In lifting a car, the total mechanical energy input of a hydraulic hoist is 5.61 times 10 to the 4. Okay? Now, if I didn't know right off the bat that that was EI just from reading the question, all I'd have to do is look at the other number and know that the biggest one is always EI. Okay? That's the bigger of the two. Okay? So we'll just write it out as 56,100 joules. Okay? The useful mechanical energy output, okay, is 19,600 joules, and we're looking for the percent efficiency. So percentage will be then 56,100 on the bottom. All right, 19,600 divided by 56,100, okay, and that'll give us our percentage there. So 35% efficiency for that one. Okay, how many people have done number 3? Yeah, let's go over that one then too. All right, small electric motor has an efficiency of 85%. Okay, in lifting a small load, it produces 15 joules of mechanical energy input. Okay, calculate the useful mechanical energy output. All right, so percentage equals, okay, EM over EI. And this time, I'm looking for the top number, okay, the smaller of the two. So I'm going to multiply EI by the percentage. And that also makes sense. If I multiply a number by a decimal, it gets smaller, right? If I divide by a decimal, it gets bigger. If I multiply by a decimal, it gets smaller. Okay, so I take my 15 joules and I multiply that by 0.85, okay, and I'll get a number that's smaller. Oops, not divide, times. 12.75 joules of useful work. Okay, I'll give you a couple more minutes to finish those up, and then we'll go over the rest of them together. Okay, so have a look at these ones here. So in heating a pot of water, 2,000 joules of heat was supplied by the stove element. If only 500 joules of heat was actually gained by the water, what was the percent efficiency of the stove element? So percentage, okay, we're looking at the smaller number, 500, okay, our useful work divided by 2,000, the amount of work that was put in, okay, and 5,000 over 2,000 should be 25%. Am I right on that? I'm just doing that in my head, okay. For number 5 here, a Bunsen burner supplies 4,000 joules of energy to a small beaker of water. Okay, so it's exactly the same as the last question. That's really silly. Okay, so we would have, for that one there, percent efficiency would be 125 joules divided by 4,000 joules. Okay, that's going to be a pretty small number. Come on. Okay, so 3% efficiency for that one. Okay, and for number 6, calculate the percent efficiency of an engine that consumes 3.5 times 10 to the 3, or 3,500 joules of energy, in only doing 2.3 or 2,300 joules of work. So we would have our 2,300 over 3,500. Okay. Sorry, 2,300. So that's a very efficient car because it's running at 66% efficiency. Okay, on that one. Now the last one is the one that's tricky. Okay, it's not really all that hard. It's just sorry, number 8's the one that's tricky. Okay, percent efficiency of a machine is 35%. All right, so they tell us the percentage is 0.35. Okay, what's the useful work done? So we're looking for EM here. If it consumes 12,000 joules of energy. All right, so we've got EM over EI equals the percentage. So if I multiply both sides by EI, okay, I'll have my number there. So 12,000 times 35% is 4,200 joules of useful work. Okay, questions on that one? Okay. Now, number 8, the one that's actually tricky. Okay, the only reason that this one is tricky is because you actually have to calculate what the useful work output was before you put it into the efficiency calculation. All right, so the question tells us that the efficiency of a machine is 35%. So they tell us that. We've got 0.35 here. Okay, and it's moving a 2,000 kilogram object to a height of 5 meters. Can I figure out how much the energy of that object is changed by? By doing what? Right. Find the change in gravitational potential energy. Okay, it was lifted 5 meters. I'm just going to assume it was on the ground when we started. Okay, and find out how much potential energy it has when it's at 5 meters, because the change in potential energy will equal the useful work that was done in lifting it 5 meters. Agreed? Okay, so we'll simply go 2,000, the mass, times 9.81 times 5 meters. All right, so there's our useful work. Okay, so that's the top number, and we want to find the bottom. Well, they told me, okay, that it was operating at 35% efficiency, so I know I'm looking for the bigger number. I'm going to divide by 0.35. Okay, there's how much energy would have actually had to be put in order to get that to happen. Okay, questions on that? There won't be any problems in the written response section of your test on efficiency. I think I just made 2 multiple choice questions on it. Okay, so because it's a pretty simple calculation, it's not something I'm going to waste a 5-mark problem on. Okay. Questions on any of that? Okay.